Okay, hello everybody. I guess we're ready to get started. Thanks for attending this webinar, Accelerating Deep Learning for Embedded Vision at the Edge. My name is Hugh Pottsmith from CMC Microsystems, and I work in the Embedded Systems group at CMC. Okay, so the objective of this webinar is to demonstrate an integrated machine learning, training, and inference flow that utilizes tools and hardware that are available to researchers in Canada's National Design Network, namely Xilinx tools and platforms and heterogeneous computing platforms. This webinar builds on a previous webinar that we presented in February called Accelerating Deep Learning for Vision using Caffe, which presented some of the infrastructure for the training phase, and that's available on our YouTube channel. I would also note that this work was partially supported through a national defense project through their IDEAS program. In terms of the agenda, I'll give a brief introduction to CMC and provide an overview of the application that we used. I'll then describe the hardware and software environment that we used in the flow to train and quantize the convolutional neural network, and then show a video demonstration of the application in operation. I'll conclude with information on how to access the tools and equipment, and then allow time for question and answer. About CMC Microsystems, CMC is a not-for-profit corporation that was incorporated in 1984, and we're the manager for Canada's National Design Network, or CNDN, and we deliver micro and nano innovation technologies and capabilities across Canada. The National Design Network is a Canada-wide collaboration between 66 universities and colleges and growing, which connects 10,000 academic participants with 950 companies who are designing, fabricating, and testing microsystems prototypes. CMC measures the outcomes of the National Design Network through the research and commercialization outcomes from its participants. So in terms of research outcomes, we look at journal and other publications, research awards, and HQP generated through graduate and undergraduate courses. And for commercialization, we measure the number of startups, patents, licenses, and industrial interactions that are enabled by the infrastructure that CMC provides. The infrastructure and services we provide is divided into three main categories. CAD, which delivers design tools and environments, platforms, and training, as well as compute infrastructure to develop, design and develop micro and nano system prototypes. We deliver this capability through cloud infrastructure or on the user's desktop. We also provide fab services, which provides multi-project wafer services, package and assembly, fabrication and travel assistance to manufacture prototypes in commercial or university-based labs, and lab services, which provides short-term access to development platforms and test equipment to validate, emulate, and test prototypes. The technologies that CMC supports include microelectronics, photonics, MEMS, microfluidics, and embedded systems. To deliver that capability, CMC engages with partners across Canada and around the world, working with CAD vendors and other technology suppliers, M&T labs and commercial fabs, other nonprofits, and other partners. Given the large national scope, the National Design Network, Canada's National Design Network community spans many application areas, design-oriented interests, and disciplines and departments. Some key large groups are the ICT and biomedical community, design in embedded systems, digital and embedded software, and the electrical and computer engineering departments. Given that a large part of our community uses CAD tools, which are funded through a CFI project called ADEPT, I'd also point out that CMC and a standing committee of academic and industrial advisors are developing a follow-on proposal to the ADEPT project for the upcoming Infrastructure Fund 2020 competition. This new project is called CADnet. and Canadian Design Network for Circuits and Systems, and this will deliver $20 million worth of design infrastructure to up to 40 institutions and faculty following the completion of the ADEPT project in 2021. This includes CAD tools, compute and license servers, FPGA platforms, and an online hardware emulator for accurate ASIC power and performance estimation. More details are provided in CMC's community space, or you can contact me for details and to check if your institution is participating in this project. I'll now describe the application, I guess, for our demonstration. So this is the requisite slide that states that AI and machine learning has exploded in commercial and research interest, in large part due to new computing architectures such as GPUs, FPGAs, multiprocessors, and specialized ASICs that can handle the scale of computations to make machine learning available to many industrial applications, such as autonomous vehicles, robotics, and advanced manufacturing. A common implementation of machine learning is the convolutional neural network, or CNN, and there are many existing and emerging examples and ecosystems of tools and platforms for CNNs targeting problems such as object detection, character recognition, and natural language processing, to name a few. Increasing machine workloads are moving from cloud-based processing to processing at the edge, close to the sensors in applications such as autonomous driving and sensor fusion. For example, in driver assist vehicles and tasks such as pedestrian detection, these systems take input from a number of sensors, which could be LiDAR, radar, camera vision, and they need to react quickly and correctly. Edge computing provides lower latency and fast response needed compared to sending data to the cloud to process and then send a response again back to the edge. But this also presents challenges in terms of power constraints and harsh environment operation. One of the aspects we've been exploring at CMC has been heterogeneous computing, and more recently applying heterogeneous computing architectures to both the training and inference phases of machine learning. On the server side, we've used a heterogeneous processing platform which combines FPGAs, GPUs, and Xeon Phi accelerators, and to accelerate the learning and inference in the cloud. And we're also exploring platforms that use embedded platforms that combine multiprocessors and FPGA programmable logic. Some of the advantages of reconfigurable and heterogeneous computing: these systems offer flexibility to target parts of the algorithm in software and parts in reconfigurable hardware or specialized accelerators to achieve performance speedups, lower latency, and power efficiency while maintaining software programmability. These also allow designers to scale up or scale down to meet higher performance or lower power requirements by selecting components from the same family of chips, which may have more or fewer resources while maintaining the same design flow and architecture. FPGAs, particularly FPGAs with programmable hardware, allow for in-field modifications without changes to the existing equipment. This can allow the incorporation of new network models, new applications, better trained models, and also continuous learning where the model can be updated on the fly. The diagram here presents the development flow that we use for this project. The first step is dataset curation, where we select a training dataset that demonstrates the problem we're trying to, or the objects that we're trying to detect in this instance. The second phase is to select a network, a CNN architecture appropriate for the problem. In our case, we selected PASCAL VOC for a training data set and SSD 300 for the CNN. The next phase is training, which uses the annotated training data set to determine the weights in the CNN by comparing the result of running data through the CNN with the expected results and making incremental adjustments until the error is acceptable. For training, we run on a heterogeneous processing platform, or HPP, which we've delivered through the previous previous CFI project called MPSoC. And we were also introducing a heterogeneous compute cluster, which has FPGA and GPU accelerators available in the cloud. These platforms include multiple processors, GPUs, and FPGAs to accelerate training and validation. Once the training is complete, the result is a floating point model. To run on the embedded FPGA target platform, the floating point model needs to be converted to a fixed point model. In our case, we're using 8-bit integers. Once this is completed, the fixed point model can be implemented on the FPGA fabric and then process new images or video frames. This operating mode is called Inference. So we go from a floating point model to a fixed point model. In terms of our application, we're demonstrating is video-based object classification and detection. We'll take a frame from an incoming video stream, such as a camera, identify multiple objects in the frame in the scene based on the training data set, and mark each object by color-coded bounding box, which encloses the object. The CNN that we used is called SSD, or single-shot multi-box detector, which is a common data or common CNN for object detection and classification tasks. It was introduced in 2016 and achieved new records in terms of performance and precision for object detection tasks, scoring over 74% mean average precision in the standard data sets such as PASCAL VOC and COCO. The first layers of the SSD network are based on another CNN called VGG16. The reason why this was used is because it has strong performance in high-quality image classification tasks and its popularity for problems where transfer learning helps in improving results. The CNN takes as input a 300 by 300 pixel image or frame. It will output classification identifiers of the objects detected in the frame, as well as the location of those objects in terms of coordinates for bounding boxes. As I mentioned, we selected the PASCAL VOC, or Visual Object Classes dataset. This is a commonly used and freely available data set with standardized image for object class recognition. It contains over 20,000 images containing over 45,000 annotated objects. This data set includes 21 different classes of objects, such as airplanes, cars, people or pedestrians, various animals, and objects that could be detected within a frame. So I'll now just mention the hardware and software environment that we used to develop our demonstration. For training, we used two workstations or servers that we had available. One was a workstation that had been distributed again through the MPSoC project and is available at some institutions across Canada through that project. And this is a workstation which had a dual-core Intel CPU, an NVIDIA Tesla K40 GPU running Ubuntu 16.04. The other server we had was a more recent server that had a newer generation NVIDIA GPU, the Tesla Pascal P100. And as I mentioned, and I'll mention towards the end of the presentation, we're also introducing this on a heterogeneous compute cluster, which will be available for cloud access. For inference, we use the Xilinx Zyng Ultrascale MPSoC ZCU102 development kit. Again, this is being made available through the MPSoC project and is available at various institutions, as well as through our equipment pool. We also tested a FMC camera that can be mounted on the board and an HDMI monitor to display the output. In terms of software, the core tools, I guess, are from Xilinx. We used Xilinx's Deep Neural Network Development Kit. And this uses underneath or complementary Xilinx's SDSoC development tool, special SDK for DNNDK and for the ZCU 102 board. We also used other software packages for machine learning, such as the Caffe machine learning framework and various libraries from NVIDIA for GPU acceleration. Xilinx DNNDK is a relatively recent tool from Xilinx. This is a full stack software development kit for their deep learning processor unit, or DPU. This was originally created by a company called DeFi, which Xilinx acquired last year. DNNDK supports network quantization, compilation, optimization, and runtime support to run on Xilinx Zyng Ultrascale MPSoC chips. DNNDK originally supported only the Caffe framework, but the latest release now includes or supports TensorFlow, which is an uncommon framework for CNNs. DNNDK supports a number of Xilinx development boards through board support packages, including the ZCU 102, but there's also the ZCU 104 and Ultra 96 boards are supported. The Deep Learning Processor Unit, or DPU, is a coprocessor for the embedded ARM core that's on the Zyng Ultrascale MPSoC chip. It offloads commonly used network layers to be accelerated in the FPGA fabric rather than running in software. The DPU supports multi-threading, and depending on the Zyng chip selected, can support up to 4 DPU cores on a chip. For example, the Zyng part on the ZCU 102 board can support 3 DPUs. Another capability that is unfortunately not provided in the free version that we used is a network pruning tool. This allows the designer to explore removing nodes and connections from the network that will not significantly impact the accuracy, but can greatly increase performance. This will reduce the size of the model and the number of computations required, resulting in lower power and higher performance. However, it's not currently provided in our license set, although we'll pursue with Xilinx to make this available. Most of the flow that we used is described in Xilinx's Edge AI Tutorials GitHub at the URLs shown here. They also provide other tutorials for the CFAR10 dataset, an AlexNet-based CNN, and a DPU integration lab. They also have an active forum for DNNDK, which is their main support mechanism. In terms of the inference hardware, as I mentioned, we use the ZCU 102, and this features the Zyng Ultrascale MPSoC chip, which has a quad-core ARM A53 application processor unit, a dual-core ARM real-time processor, a ARM Mali 400 GPU core, plus FPGA fabric, which includes memory, DSP, and high-speed serial I/O blocks. The board also includes DDR4 memory for processor and FPGA, FMC expansion connectors, video I/O, SD card slot, UART, and Ethernet connectivity. To make the board's video interfaces easier to incorporate into user applications, Xilinx developed the Revision Stack framework. This is a pre-built platform for embedded vision applications. This platform includes video capture and sync pipelines, implemented in programmable logic, and connected to the processing system through high-performance AXI ports. It also includes an XF OpenCV, which is a library of OpenCV functions that can directly generate FPGA hardware to accelerate common video processing functions. The revision stack from Xilinx uses the Gstreamer open framework to build video processing applications. This is a modular open framework that includes a large library of processing elements called plugins. A plugin can be also user-created via C, C++, Python, etc. A plugin can be a source, sync, or filter block, and in an application, plugins are linked and arranged into processing pipelines. Pipelines can be constructed and launched via application code or from a command line utility called GST launch, which is what we used in our demo. The figure in this slide represents the pipeline we used in our demo. Our video source is HDMI input. The source video is sent to a video conversion plugin to convert from YUI2 format to BGR format video. The SDX traffic detect plugin is our core processing element for object classification and detection that runs our CNN. The process frames are then output to a plugin from the Gstreamer library, which will count and display the number of frames per second, and then that will be sent to the HDMI monitor as the video sync. I'll now briefly go through the flow that we used to develop the training and inference. So this diagram shows the inference development flow. It starts from a training data set and an untrained or partially trained CNN model. In our case, this is the PASCAL VOC data set and the SSD 300 network model. The first step is training the network using the floating point version of the model. Once the network has been trained, the CNN is quantized from floating point to 8-bit integer using the DNNDK's decent tool. The resulting fixed point model is compiled into a shared library using another tool from DNNDK called DNNC, or DNNC compiler. At this point, there are two parallel development projects in the Xilinx SDSoC environment. The first project is the hardware project. In our case, it was called DPU core _ ZU9. And this describes the DPU architecture and implements the hardware that will be downloaded to the FPGA fabric. The second project, in our case called GSTSDX Traffic Detect, is a pure software project that will create the Gstreamer plugin for our object detection CNN. The DPU core project will generate a boot image for the FPGA. The Gstreamer plugin project will generate a shared library.so file. Both of these files will then be copied to an SD card, which can be plugged into the ZCU102 board. The board will boot from the SD card and then run the Gstreamer pipeline from the command line. So in terms of the steps we followed, first we installed the various tools and environments, including the Xilinx tools and the Caffe tool for SSD, and instructions were provided from Xilinx in the GitHub on what specific versions of those tools and libraries were required. The next step is to download a pre-trained version of the VGG16 network model, which forms the front end of the SSD model, as I mentioned earlier. Starting from a pre-trained network reduces the training time. You also need to download the PASCAL VOC dataset, and using scripts provided, you can create training and test databases. A Python script adds SSD layers to the downloaded VGG network and generates the files which describe the SSD 300 network, namely the proto.txt files in the fourth bullet. The next step is training the SSD network. There are some adjustments that are required and documented by Xilinx for compatibility with the downstream DNNDK quantization and compilation tools. This is a matter of changing a few layers in one of the files. This training, once the adjustments are made, a script will run the training. The script gets shown here. This training runs for 120,000 iterations. On the older workstation with the NVIDIA Tesla K40 GPU accelerator, this took 6 days to complete. On the newer workstation with the Tesla P100 GPU, it was 3 times faster and only took 2 days. Our next step will be to run on the heterogeneous compute cluster and see if that is further accelerated. At the end of the 120,000 iterations, the network is assessed with a test data set and achieved an accuracy of 76%. And then it generates the Caffe model and solver state files for those 120,000 iterations. It also takes snapshots at 80,000 iterations. You can run inference on the workstation using the floating point network to verify the results. There are scripts as well to run that. Again, this achieved about 76%, and you can also run it on specific images, and it will output the classification and the bounding box for the images. The next step, once the floating point network has been trained and validated, is to use the DNNDK's DCENT tool to perform quantization and generate a fixed point version of the model. To run quantization, you need the floating point model files, the Caffe model and proto-txt files, which were created earlier, or developed earlier, as well as a small calibration data set of 100 to 1,000 images. The output of the command will be fixed point versions of the Caffe model and proto-txt files. You can invoke GPU acceleration from the command as well as an auto test sequence to test the accuracy of the fixed point model. As you can see, the auto test achieved an accuracy of 79% on the calibration data set. Although DCENT can generate models for arbitrary bit widths, the current version of the DPU coprocessor only supports 8-bit values. Once the network has been quantized, it's compiled into a shared library using the DNNC tool. The output of this command is an ELF file. And then an additional step to use the model as a Gstreamer plugin is to compile into a .so shared library file, which can then be used in the SDSoC environment. As I mentioned, there are two parallel development phases in SDSoC. The first one is to create the hardware, which is the DPU core project. And the second one is to generate the Gstreamer plugin, which runs on top of the DPU processor, or runs on the ARM processor, accelerated from the DPU. So the first project is highlighted in red and generates the hardware. It's described in C, C++ and uses Xilinx high-level synthesis tools, or HLS tools, to automatically create the hardware. As you can see, it takes a considerable time to generate that hardware, 3.5 hours, depending on the workstation that you're using. But once you generate the hardware, you don't have to regenerate it every time. The second project is the classification and detection plugin. Again, this is in C, C++. And this is purely software running on top of the DPU hardware. Therefore, it only takes a matter of seconds to recompile the plugin application. It shows the advantage of this approach. You can develop and modify your plugin application and validate and run on the hardware platform quickly without a lengthy hardware compile step. So this is built in SDSoC, but it also generates a Xilinx Vivado project, so you can view the implementation results. By default, the SDSoC project generates 2 DPUs in the available FPGA fabric. You can see from the implementation results, this results in 62% utilization of FPGA LUTs, 56% utilization of flip-flops, 77% utilization of the block RAM, and 53% utilization of the DSP blocks. Note that this also includes the hardware associated with the revision stack framework, including the HDMI input and output pipelines and the FMC camera interface. And the power estimation from the Vivado tools for this design is a little over 20 watts. So the next step is to copy the files that have been generated to an SD card. Some of the files are pre-built from Xilinx for the ZCU102 board. These include some utilities for the DPU processor. From the DNNC network quantization and compilation step, you copy the .so file that was generated there. From the DPU core hardware project, you copy the boot image as well as the a library file for the DPU core, and then you also copy the shared library file for the traffic detection Gstreamer plugin. These are copied onto the SD card and plugged into the ZCU102 board, and the board boots with a Linux image. And from a terminal window connected to the board, you can then issue commands to run the inference. As I mentioned, Gstreamer has a utility called GST launch that can set up a pipeline from the command line. We created a script just to simplify things, because the command, depending on the size of the pipeline of the command, get quite burdensome. So there's a few commands. The video._cmd sets up the video input and output, and then the GST launch will set up the pipeline and start the pipeline processing. So again, you see the video source from HDMI conversion, and then the CNN processor plugin outputs to the frames per second display block, which then outputs to the HDMI monitor. And the result is shown here. You have the HDMI video input, and you have the HDMI video output on the monitor, which includes the bounding boxes that are color-coded based on the classification. So people are color-coded as yellow, and cars are color-coded in magenta. So I'll now just show a quick video showing the demonstration in action. So the video shows the setup of the demo. We're using the laptop as a video source via declaring our screen to the HDMI output to the 102 board. The processed video frames are passed to the HDMI output port, again through the revision stack, which is then displayed on the monitor. Here is the ZCU102 board with the FMC camera mounted. It's not being used in this example, but we did test and validate it. As I mentioned, there's a Linux kernel that is launched, and you can go to the SD card directory and look at the files. In the lib directory are all the different model files. Some of them are pre-created from Xilinx for the various CNNs. And then you can look at the script that we use to launch the inference, including the GST launch command. You can also use the video command to list the available video sources, and then ultimately launch the inference demonstration. And here is a side-by-side of the input video and the processed video. You can see from the frames per second that it's running at 3.24 frames per second, and it is drawing the bounding boxes around the detected objects. And this includes various types of objects that were provided in the data set, and does a reasonable job of detecting those objects, although the performance could be improved. I'll now mention how to access these tools. So the Xilinx tools are available from CMC. The SDSoC tools and licenses are available for academic use. These are available through local and also CMC cloud installation. As I mentioned, the ZCU 102 MPSoC development kit has been made available through the CFI, the MSysCan CFI project. There's a link in our community for our community space for the development systems, and this will list the locations and contacts at each institution that has these. We also have a number of these platforms available for short-term loan in our equipment pool, and the loan terms are around 6 months, or if needed longer, that can be arranged. The HPP that was used in the training phase was also provided through the MSysCan project. The platforms include FPGA accelerators, NVIDIA Tesla K40 accelerator, and Xeon Phi as well. And more recently, CMC through a follow-on CFI project called Adept installed a large compute infrastructure at University of Waterloo for access by researchers in Canada's National Design Network. This is a secure and remotely accessible CMC cloud infrastructure, which includes virtual machines for running instances of pre-installed design environments for ASIC and FPGA, TCAD and multiphysics tools and environments. There is also a compute cluster for accelerating simulations and CAD tools, and a heterogeneous cluster combining GPUs and FPGA accelerators. So the compute cluster is a dedicated group of servers enabling researchers to improve the performance of large computation tasks, including Xilinx tools. This cluster consists of 8 nodes with large compute memory and storage resources. And more specifically relevant to this demonstration and this tool set, I guess, is an FPGA GPU cluster that has been recently installed and will be shortly available for researcher access. This is a cloud-based, remotely accessible compute infrastructure specifically designed to accelerate compute-intensive applications such as machine learning training and inference. It includes the latest state-of-the-art acceleration technologies, including the latest generation of Xilinx FPGAs, Alveo U200 boards, and NVIDIA V100 GPU boards, and massively parallel processing units closely coupled with server processors and a software stack consisting of a complete ecosystem for machine learning frameworks, libraries, and runtime targeting heterogeneous computing accelerators. So our plans would be to port the training environment from the HPP workstations that we use to this cluster. The cluster consists of 8 nodes with combinations of the Xilinx and NVIDIA boards. In terms of deep learning frameworks, this cluster supports TensorFlow, Caffe, MXNet, and can be used for both training accelerated by the GPU and inference on FPGAs or GPUs. More information on this cluster is on the CMC website. So in summary, we presented a flow for convolutional neural network training and embedded inference, which used the Xilinx DNNDK and Zyng Ultrascale plus MPSoC development kit. This is a fast, streamlined flow for rapid prototyping of embedded inference, and it used tools and equipment that are available through CMC. In terms of future work and development, we'll continue to explore this environment and look at performance improvements, including introducing the network pruning tool to improve performance, looking at the DPU core supports multi-threading. So, and as I mentioned, multiple DPUs on the same FPGA fabric. So we'll look at accelerating algorithms using multi-threading and multi-DPUs. We'll also look at implementing other networks and models on the same infrastructure. As well, if there's interest, we would run training on the Xilinx SDSoC environment, the Zyng Ultrascale plus MPSoC and the DNNDK environment for users. As I mentioned, we'll shortly release the CMC Cloud Heterogeneous Computing Cluster and port the training environment onto this cluster. We're also, in addition to an FPGA-based AI inference flow, we're looking at an AI flow that would target an ASIC reference design that could be manufacturable in silicon. And we're interested in your opinions on this, and if you're interested in being a lead client or an advisor to any of these projects, please let me know. And that concludes things, unless people have questions.
Yeah, we've had a few questions come in. The first question is, why is the output frame rate pretty low?
I think because we do need to still explore how to optimize the network through the pruning tool, at least according to the Xilinx marketing information. We could see a fairly significant speed up from what we have. That's my best guess, I guess.
Okay. How much is the maximum speed of moving objects that can be detected? What's the maximum speed of moving objects?
We haven't measured that.
Is that something?
Unless it's, well, maybe it's more specific to the SSD network or something like that, but we haven't measured that.
Okay. What was mapped to the ARM cores and what was mapped to the FPGA fabric?
In terms of the ARM cores, most of the Gstreamer plugin setup was running on the ARM, and then certain layers, and I can't remember off the top of my head, but some layers of the network that aren't readily acceleratable, I guess, on the fabric are run in software, but then the layers that are, I guess the DPU is suited for accelerating are run on the FPGA.
And do you have control over the mappings?
Yes, I believe so, because basically there's a whole SDK for the DPU, so you can write your code and create threads and farm threads out to the DPU through coding. We just didn't explore it too much, but it's feasible.
And assuming that if the maximum speed hasn't been measured yet, the maximum size of the objects probably hasn't been measured yet either, or is there?
No, we haven't measured that either.
Okay, what is the performance of the AXI port?
High? I can't remember offhand.
Does that impact the frame rate?
It would, but it's using the highest performance port available on the chip. So I think that's as good as that pipeline's going to get. I know without the CNN processing, you can run at full speed, 60 frames or whatever it is. So it's the actual CNN that I think is slowing down the overall performance.
And another question, can we use VHDL implementation of CNN instead of the model generated by the tool and still use the rest of the setup?
Yeah, you can. We looked at, there was another project from Xilinx called CADnet, which used high-level synthesis to generate a hardware accelerator, which is, I guess, equivalent to maybe a pure VHDL implementation, and that can be implemented in the same framework.
And how to measure performance or watt of your mapping?
Offhand, I guess you can get modules to measure the either TI or some other vendors that you can plug onto your board, and they'll measure the power or the voltage usage on the fly as it runs. We just haven't had a chance to do that yet.
And one final, this is connected to another question, but this is or the use of the Vivado power estimation tool. I'm assuming these are all modular, so they can. As
a software tool, I know it exists. I haven't used it before, so I don't know.
Okay.
You can run it on the fly, or if it's just Vivado, if it includes, if you can run it with Zyng Ultrascale, because then you have both the processor and the FPGA logic.
Okay. There's a suggestion that a hands-on workshop might be of value.
Good. Would enjoy giving one.
Okay. And a suggestion to add hardware-software block diagram of what was mapped to hardware and what was mapped to software. Sure. And the performance for watt.
Yeah, that makes sense.
And I think that is everything.
Well, if anyone has further questions or wants more information, my on the slide. Yeah, you can contact me by email with any questions or if you want any further information.
Great.
Thank you very much.